The next step will be to join the attention blocks together and to make the decoder model or the classifier for the token sequence. However, before we can do that, there is some obstacle to overcome. How the token sequence arrived. You see, like in a sentence "hello," if we consider in this particular case, let's just consider each single character is a so-called token. This is to remind you sometimes if you process the data in another way, you might as well to treat each word a token. This is also okay, but just for example, let's consider each of those characters a token. It is of course we cannot let the numerical model to directly handle those characters like H, L, E. But of course we can give them each a number, such as if we start from A, let A to be 0, then we will have H to be 7, or when we have arrived 25 for all the English letters, we can start from 26 for the lowercase ones, so on and so forth. Fine. And then this will convert to something like 7, maybe 32, 33. I don't know. So that does not matter too much, but this is just a sequence of integers. However, what does our model expect? It expects a sequence of tokens in this way. And each of the token needs to be represented in some kind of mathematical form, a vector. It needs to be in some, like each token needs to be like an item of a data for its own sake. So we need to do some mapping from integers into vectors. The way to do that is to employ a dictionary, and this dictionary contains all possible tokens. For the English letters, maybe we have 52, and we need to include all possible outcomings of those characters, such as including the comma, includes all the different, includes the space, includes the comma, period, so on and so forth. So maybe let's just, for example, see there are 7 different possible characters, tokens in this way, and we give them each a numerical vector to represent them. This is called embedding. There are good papers out to discuss this problem. And here we employ the most straightforward method. We let those embedding numbers to be learned as well. So this operation is called an embedding layer. So this is how we do that. Given the data, and the data consists of embeddings, okay, and the excuse me, embedding is done using the token embedding, and this is initialized with, of course, the vocabulary size, how many are all the possible tokens, and the dimension of the feature vector. And for this reason, this C is called embed dimension in our configuration. Okay, and Beyond this, besides of this embedding, to emphasize the fact that different tokens appear at different locations in a sentence. Okay, for example, when it comes to some English word, it could have different meanings when it appears at different locations, positions in the second in the sentence, or alternatively, consider the word maybe H. The way it combines to other words is different when it appears at the beginning of a word, or it is appear following other words in other locations of the word. Okay, so to emphasize this kind of information, we do not only have one piece of information in the embedding vector. So this is an element-wise addition to another embedding vector. So the final embedding will be the sum of these two vectors. For this embedding vector, it will encode the location at which the token appears in the sequence. It embeds the location in an extremely easy way. For each of the dimension in the vector, so look, okay, I think I kind of linked two different objects, because remember that I have said this is the embedding dictionary that represents all the dictionaries. Actually, after the token sequence comes, we need to look up this dictionary and use this dictionary to form an embedded token tensor of the same length of the sequence, right? And for the location embedding, so the addition happens here, we just prepare a fixed tensor for the longest possible sequence. So this is max length of the sequence. And now look, each dimension of this vector goes goes in a way that represent different locations of the sequence. So if let us draw this in a different way. Here, okay, I can put numbers here by giving a kind of function that represents location in this direction. This goes to the token position. So for example, I can use a sine function, and for the second vector, I can use a sine function maybe of a different frequency, and combined together for each location, it will be represented by a tuple of numbers that is unique to that location. So that is called position embedding. Okay. With the position embedding, and the token embedding with another dropout, just as we have discussed before, we get the input representation of the sequence, the token sequence. Okay, and we do the attention blocks of this. Okay, this is a heavily loaded one-liner. This consumes most of the computational time because the blocks is constructed using the attention block, okay, and it's for this number of times. So we stack a number of the previously discussed attention blocks together, and for each time we create an attention block, and we put this together into a sequential of processing steps, and we use this to process X. And after that, we do some linear normalization again before we put that into the final classifier. Okay, after the final classifier, it will be transformed into a collection of probabilities. So look, the dimension of the input of the classifier head is the embed dimension, and for each position of the sequence, it will generate a probability vector or the probability score. Basically, this is not strictly probability because it hasn't been normalized, but the size is the same as the vocabulary size. That means how likely, how plausible for the classification result at this location of the sequence to be each individual entry of the vocabulary. Okay. So just another illustration. I think I need more space maybe. Here. Okay. Okay, change the color. This is a finally transformed representation of the data, and then it is given to a head. Then it will become, so this will be the length of the sequence, and this will be the vocabulary size. So for each row that represent for this location, what would be the prediction result? The prediction will represent at this location. I would like an output with the possibility as predicted for each single entry of the vocabulary. To actually get the probability we will discuss later, we need to sample a word or a token from the vocabulary according to the predicted probability. And that finishes the processing of an input data. Optionally, when there are desired targets is given, we can compare the predicted probability with the desired targets, just as we discussed before for any kind of neural networks, and return the loss as well. So this finally completes the construction of the transformer decoder, the decoder using attention. And there is some minor helpers such as initialization of the width and some other adjustment you can do. Please read the code and play with yourself.